Hello students, I am Professor Isha Medirata from LG Institute of Engineering and Technology. We have started with the third chapter of our syllabus, that is semiconductors, and we have covered till Zener diode, which was covered in the last video. Today I am discussing another important topic of the chapter, which is known as metal semiconductor junctions. Now we have seen what a PN junction and a Zener diode is. Talking about both of them, they are formed by using two semiconductors. But this particular junction is made using a metal and a semiconductor. So it's a combination of both. Let's see what metal semiconductor junction is. A metal semiconductor junction is a type of electrical junction in which metal comes in close contact with semiconductor material. So it basically has a metal diffused with a semiconductor. That is what forms a metal semiconductor junction. You can commonly say metal semiconductor junction is known as an MS junction also. Now, talking about the metal semiconductor junctions, they can be either rectifying or non-rectifying. What do you mean by the word rectifying? Rectifying junction is a one which allows current flow only in one direction, whereas non-rectifying allows current flow in both the directions. Talking about the semiconductors used here, we use particularly N-type semiconductors. Why? Because N-type already has majority as electrons. The common metals which are used in MS junctions are platinum, molybdenum, chromium, tungsten, all of them having high conductivity. Before I move on to the categories of metal semiconductor junctions, let us discuss two important terms which are related to this topic. First of them is known as work function, which is denoted as phi. What do you mean by work function? It is actually denoting a type of energy only. So it is the minimum energy which is required to transfer an electron from a point within a solid to a point just outside its surface. That minimum energy is known as work function. The second term which we are going to discuss is electron affinity, which is denoted as chi-n. It is the amount of energy released or spent when an electron is added to a neutral atom or a molecule. If you are adding an electron to a neutral atom, what will be the amount of energy released? That is what is denoted by electron affinity chi-n. So basically both the terminologies are related to energy only. Now let us classify the metal semiconductor junctions. So their classification is, one of them is known as a Schottky junction. A Schottky junction is the one which has phi m greater than phi semi. What does this mean? The metal which is used to make the Schottky junction has a higher work function as compared to the semiconductor used. We'll be seeing in detail. Let's see the second category of metal semiconductor junctions. It is known as an ohmic junction, which has the condition phi m is less than phi semi. What does that mean? The metal which is used to make this type of a junction has a lower work function as compared to the semiconductor used. So now let's start with the first type of junction, that is Schottky junction, in detail. Now this particular junction is known as a rectifying junction. Let's see why it is known as a rectifying junction. So what is a Schottky junction? It is formed when the work function of metal is more than the work function of semiconductor. And this was the condition which we have just seen, phi m is greater than phi semi. Next, this is how a Schottky junction is explained. So I will be explaining it before the contact is made. So in this diagram, you can see the energy band diagram of metal and semiconductor separately. And then we'll be discussing what happens when the contact is made. So before the contact is made, you can clearly see here that metal, the gray colored portion indicates the levels of the metals that are filled up. And above that, the white colored portion indicates the empty levels. And this is what is indicated by the work function. Besides it, on the right hand side, we see an N-type semiconductor. Now we know that N-type semiconductor has donor atoms added. So the conduction takes place between the donor level and the conduction level. And so the Fermi level, which is indicated as EFN, lies closer to the conduction band. Because we are talking about n-type semiconductors, we have electrons as majority which are present in the conduction band. The valence band is completely filled up with electrons, but the electrons which are present in the conduction are because of the donors added. So this situation holds true if the contact is not made. And here what do we have? We have a Fermi level of metal and a Fermi level of semiconductor. Now let us discuss the second case when the contact is made. Now in my previous video, while explaining PN junction diode, I explained you that when you talk about energy band diagrams of a junction, the Fermi levels should line up. That means here we have one metal and the other semiconductor. So when you make a junction, both of them should have Fermi level at the same level. And that is what is indicated in the second diagram here. You can just see EF, that is the Fermi level of metal, and EFN, that is the Fermi level of N-type semiconductor. They both share the same level. And because of this concept, you can clearly see that the maximum level of metal is at a height. And if you talk about the maximum level of semiconductor, it is somewhere down. And this is what creates a depletion layer. In other words, I can say when you diffuse both of them. Now you must be wondering that metals are conductors, so they have more electrons. But when you make a junction of a metal and a semiconductor, particularly N-type semiconductor, wherein we say that metal has a higher work function, so obviously the semiconductor is going to give electrons. Why? Because it has a lower work function. So when you fuse both of them, it is easy for electrons to come out from semiconductor as compared to the metal. But semiconductors donating capacity is less and metals accepting capacity is more. So what happens? Not only close to the junction, but from deep within the semiconductor, the electrons move on the metal side. And that creates a depletion layer, but you can see from the diagram the depletion layer is created on the semiconductor side. In other words, I can say a region which is devoid of electrons is created on the semiconductor side. Now let us understand the working of Schottky diode. So Schottky diode working is again divided into forward and reverse bias. So here let us discuss what a forward bias is. So forward bias condition means you connect the positive terminal of battery to the metal and negative terminal of the battery to the semiconductor. Now before any external supply was connected, there was a depletion layer formed in the semiconductor. Because of that depletion layer, remaining electrons were not able to move to the metal. And so there was no continuous flow of current. But in this particular case, what happens? We have connected the negative terminal to the N side. That means this negative terminal will move the electrons towards the metal. That or I can say the barrier reduces as V0 minus V external into E. That means whatever the barrier V0 initially was there, now that reduces. You can also see the steep or the slope has reduced and the electrons are moving on to the metal. That means I say there is current. There is a continuous flow of electrons from N-type to metal. Now let's see the second condition of a Schottky diode, which is known as reverse bias condition. In this particular condition, what is seen? The external battery, that is negative terminal, is connected to metal and the positive terminal of the battery is connected to N-type semiconductor. So now what happens? Because the N-type semiconductor is connected to battery's positive terminal, the electron, instead of moving towards the metal, now it moves away from the metal towards the battery. So in this case, what is happening? The depletion layer is increasing because the electrons are moving away from the junction. And so the electrons are not able to move and recombine with the metal. And that is the reason you do not get current. Also, you can see in the diagram that the barrier has increased by E V0 plus V external. So already V0 was the barrier and V external is adding on to it. And so the slope also increases and the electrons are not able to move towards the metal. You can see in this diagram that the Fermi level is also shifting down. What does this indicate? The shifting of Fermi level indicates that there is no current. This is about the reverse bias. Now, because it allows current only in forward bias, not in reverse bias, we say that a Schottky junction is a rectifying junction. Moving ahead, what is a Schottky diode? Now, because this junction has a property of rectification, of rectifying, it is used to design a device which is known as a Schottky diode. So a Schottky diode is a metal semiconductor diode which has a low forward voltage drop and a fast switching speed. Unlike the PN junction diode, it comparatively has lower values of threshold voltages. How do we denote a Schottky diode? Schottky diode, you can just see instead of a simple vertical line, you have an S. This indicates Schottky diode. So this triangle means the anode and the S indicates the cathode or the negative terminal of the Schottky diode. Let us see the construction of Schottky diode. So you have an N-type silicon substrate, particularly N-type semiconductor. Then you have a metal on the top. Now particularly to make the two terminals, on the lower portion of the N substrate, you have a metal layer through which you get the cathode terminal. Why do we use a metal? Because it has a higher conductivity. And on the top portion of the metal, you have a gold leaf contact. Gold or platinum is generally used because they have higher conductivities. So this is how a Schottky diode is constructed. Now let us see IV characteristics of a Schottky diode. So if you talk about IV characteristics of a Schottky diode, and we know that we do not get current in reverse bias. So you can see in the graph, you have only forward characteristics. Just look at the value of threshold voltage. It is very, very small compared to silicon and germanium. So 0.2 volt is the voltage around which you get a sudden increase in current. And that is the reason we say they give us fast switching action. Let us now see some applications of Schottky diode. With the first one, they are used in high frequency switching action and rectification. They are also used in clippers and clampers, and they are used in detectors and digital logic gates. So it has more or less the same applications like a PN junction diode, but they have a low voltage drop and a very high or fast switching action. Let's move on to the second type of junction, metal semiconductor junction, which is known as an ohmic junction. It is also called a non-rectifying junction. Let's see why it is known as a non-rectifying junction. So particularly if you talk about an ohmic junction, it is formed when the work function of metal is less than semiconductor. Schottky junction was the one which had a higher metal work function, but here the work function of metal is less than that of semiconductor. What happens because of this? Just consider the condition which is before the contact is made. It is same as the one which we discussed in Schottky diode. The only difference is you can see the gray colored portion is large. That means the occupied levels are more. So only small portion indicates the work function phi m and the Fermi level as EF. If you talk about N-type semiconductor, again we have the Fermi level which is close to the conduction band. Valence band is completely filled up. The electrons which are present in the conduction band are due to the donor atoms we have added. Now let's see what happens after the contact is made. Now in this particular case, metal has higher conductivity plus metal is having a lower work function. So what will happen in this case? Before the semiconductor gives its electrons, metal will give its electrons because the work function is less. Now, the donating capacity, because the carrier density of metals is higher as compared to semiconductors, you can say per meter cube, a metal has 10 raised to 28 electrons. On the other hand, talk about semiconductors, they have around 10 raised to 16 to 18. That means metal can donate more, but the semiconductor can accept less. So just see the bridge or the junction between metal and semiconductor. You can see continuously there is a flow of electrons from the metal to the semiconductor. What does that mean? Wherever the junction is made, there will always be electrons present. So there is no such layer like a depletion layer. Instead, in this case, we get an accumulation region. We get a region which is always having electrons. We get a layer which is highly conductive, which is always present with electrons. So this is the difference between a Schottky and an ohmic junction. So let's see. Ohmic junction, because of the accumulation region, we say it has a region which has higher conductivity due to the presence of electrons. Ohmic junction acts like a resistor which is conducting in forward and reverse bias both. There is no such concept like a depletion region. There is always presence of electrons, and that is the reason even if you do not provide energy, you are continuously going to get a flow of electrons, that is current. So you can say it acts like a resistor which will only limit the current, but it will allow forward and reverse currents both. What are the applications of this junction? It cannot be used to design any diode because it gives output in both the cases, and that is the reason the applications include thermoelectric devices. So we do not have any diode like an ohmic diode, but there are applications of this sort of junctions also. So today we have discussed what are metal semiconductor junctions. We have discussed a particular diode which is better as compared to PN junction diode if you talk about low voltage drop and if you talk about fast switching action. So basically we have understood what Schottky and ohmic junctions are. What do you mean by, why do we call them rectifying and non-rectifying junctions? Hope you have understood all the topics I covered today very well. I will be starting with optoelectronic devices in my coming video. Till then, take care. Thank you.